Where is it? All right. Thank you for your patience as I deal with my technology issue. I'm really sorry about that 5-minute delay. You know, sometimes things happen. And I still need to edit a couple things because I'm literally just getting everything set up as my computer crashed right when I was about to start class. So this we don't need anymore. That has passed. We got that. 3.1 we'll be doing a week, which will be the 18th. There will be a quiz, and that'll be due on Tuesday, the 16th. There we go. And we'll talk about this quiz at the end of class. The car loan was already due. There we go. And then your next Excel is 2.1, I think it's currency. That'll be due a week after that one, which would be the 23rd. Okay. There we go. So all your due dates are up here. I'm not going to spend too much time talking about them. You should be pretty used to how this flows by now. If we do another discussion board, I'll talk about it later today. And then, of course, is always due next class. Remember, quizzes are always due next class. My math labs and Excels are always due in a week. And I'm really trying to post the Excels more than a week in advance. I feel like some students are using that to their advantage. So I want to continue to do that as I can. Okay, so last time where we left off, we said that we would do one more quick, quote, quick worksheet. That was this one. So using our CPI tables, and it doesn't have to be CPI, this could be anything having to do with ratios and proportions, but this is just one of the bigger things that we can do with that, where information tends to be laid out in a table. So we did problems 1 and 2 earlier, where we had, you know, just a euro to US dollar conversion, and we showed that that's very similar to doing a CPI from one year to another CPI from another year conversion to be able to compare the price of goods. So you can compare the price of goods from one country to another, as long as you know how many of one thing is how many of the other thing, and that's easy to find information online nowadays, and it changes every day. Or if you want to talk about the currency of one year versus another, staying inside of the same country, of course, then you can do so by having CPI values. Now, these CPI values are nothing that you would need to memorize. They are always given to you inside of problems, whether it's a table of many of them or just a small table of a couple of them. So the last problem we're going to do from chapter 2, and then we're going to go straight into chapter 3, is talking about how the CPI can be used to kind of compare how much money the federal government has collected, which they call receipts, also known as taxes. And they say that it looks like it's steadily been increasing based on the table below. So all of these numbers are in billions, and this is one thing that you've got to start learning to pay attention to. Notice how many times I've said that? I'm going to keep saying it that much. This is not saying that the US receipts in 1990 were $1,032. This says that it was $1,000 billion. Now, you need to understand something here, that $1,000 billion, change my color, $1,000 billion is the same thing as saying 1 trillion. This is something that our text loves to do. It loves to throw this at you every now and then because it can happen in the real world where you talk, okay, about 50 million, and then you get to 500 million, and then you get to 5,000 million. Well, no one wants to say 5,000 or 50,000 million or 500,000 millions. It just starts sounding silly. So typically the way we want to think about that then is in trillions, or just the next unit up or the next unit up, however many you have to go to. But that's not to say that that information is always presented to you in that way. Very often your information is presented to you in a confusing way, because that's what the media loves to do. They love to confuse and scare us, right? Okay, so please understand this is not the only time we're going to come across something like this. This is going to be a common issue. I'm not going to say an everyday issue, but common. So they say receipts, aka taxes, the money that we're paying to Uncle Sam, is going up every year, because in 1990 it was 1,000, then the next year it was 2,000, and the next year was 2,100, and again, all in billions. That's really a lot of money. So they say it's going up. It went up. It went up. But is it really going up when you consider something known as inflation, the fact that the value of our dollar changes every day, every month, every year? So the dollar generally gets weaker and weaker every day or week or year, at least every year. And again, I'm saying generally, there are times when that's not the case. So how can we tell when we were paying the most taxes, when the US receipts were the highest? Again, instinctively you'll say, oh, well, we paid the most taxes in 2005 because that's the biggest number. But that's not necessarily true in the grand scheme of things. You have to consider the fact that the value changes every year. So we need to turn these three values into currency all in the same year. Now, technically, it doesn't matter. You could, instead of finding this A and B, you could find this number, and then just compare these three. And then whichever is the biggest would tell you when we took the most money in. So if it was this one, then you'd say 2005 is when we took the most money in. Or if it was this one, then you'd say 2000 was when we took the most money in. Okay, so we could have completed this guy and compared the information. Or we could find this one and this one to be able to compare the information. But typically what's done is most people are going to think about currency in the world they live in at the moment. We're always going to think about the price of things right now, so in 2020. So that is why most people using CPI tables will generally convert to the most recent currency. But again, due to proportionality, as long as you converted everything to $1990 or everything to $2,000 or anything to the same year's dollars, you would still be able to make the exact same analysis in the same way. But again, because of the way we think, we tend to think, oh, you know, what's it cost in 2020? Because we can easily see those prices. If I want to talk about what the cost of something was in 1990, guess what? I got to look it up. And then I'm not going to have as good of a grasp on it because I wasn't even 10 in 1990. So, you know, hey, what did a loaf of bread cost then? I don't know. I'd have to look it up. What was the cost of a house then? I'd have to look it up. Okay, so we're going to use the proportion table. Now remember, these are labels. These are not numbers. Do not use the actual years. Do not use the actual years. Don't use those. Those are labels. Okay. So we're going to be using the CPI values and then these. We're sticking for that cross multiplication stuff, setting our fractions equal to fractions. We're sticking in this zone where all the data is. But I'm not necessarily saying this in my box. There's a number, there's a number, there's a number. I would be able to find this value if that was my actual box. But that doesn't do anything for us because we were told to find A and B. We were not told to complete the table. We were told to find A and B. Now, I could find that one, and then I'd have to find this guy if I called him X and Y. And again, we'd still be able to make the analysis, but I'm going to tackle A and B. So I want to try and draw a box that uses A. So I mean, if I do maybe something like this, well, no, this is a blank, so that wouldn't work. I know that was a poorly drawn box. Or you might say, okay, well, maybe I could do this. Well, no, because this is a blank and this is a blank. So that's two corners that are blanks. That's not going to work. You got to practice with this to be able to hammer it out. You're looking to draw a box with three corners with numbers and the fourth being the blank. Boom, boom, boom. There you go. There you would have this number, this number, this number, and then you'd be able to solve for your A. So drawing your box that way gives us A, and that would be 130.7 over 195.3 equals 1032 over A. And then you're going to cross multiply, which will give us the 130.7A equals, I'm going to go ahead and do this multiplication of 195.3 times 130 or times 1032. And again, I can't have a calculator on the screen at the same time, unfortunately, with this annotation mode. It sucks, but it is what it is. So if you do that product, you should get 201,549.6. And then I'm going to double check that because it's so many numbers. 195.3 times 1032. You get 201,549.6 again. Okay, so that was the product of this number and this number. So now we're going to do the division. We're going to divide both sides by the 130.7. Again, I do expect every single one of you to be able to handle this simple algebra. And when you divide by 130.7, you should get 1,542. And since everything else is in whole numbers, it's probably best to leave this as a whole or as a one decimal. It would be 1542.1 if you rounded to one decimal, 0.07 if you rounded to 2. I'm just going to stick with the whole number. So this number is now 1542. So the receipts that we had in 1990 of $1 trillion approximately. If you converted that to the most recent currency in the chart, which was 15 years ago, it was 1,500 billion or 1.5 trillion, depending on how you want to say it. So 1 trillion versus 1.5 trillion, again, just in different currencies, just in different dollars. This is like having yen and dollars. They're different things. Now I'm going to switch to blue. So now I want to find B. Now it's possible that you might be able to use A to find B. I'm not saying you can't, but there's probably a way to not have to use this number that was rounded. Now, here's a big spoiler. When you're using CPI tables, you have to use the CPI values to go from year to year, from year to year. So you're definitely going to have your box around some of these values. Well, here's the one we need, and that's at the bottom corner, so it's definitely going to have to be here. The only value that we have in this column above it is the 2025, so this is probably how we're going to need to start drawing the box. And then if I take this all the way to the left, the CPI values, you'll have two corners with numbers. So there's the box that we would draw, where you have your number, your number, your number, and your variable. So we can go 172.2 over 195.3 equals 2025 over B. And then we're going to cross multiply that. Sorry, I'm going to have to go to this side kind of. Is it legible over there? I'm just going to change my marker color. So we have 172.2b. Here's my cross multiplication for the second part down here. Equals the 195.3 times the 2025, not 202.5. That would not be right. And we get 395,482.5. 395,482.5. Let me just rewrite that. 172.2b equals 395,482.5. Then you're going to divide both sides by the 172.2. And we get 2296.6, 2297 if you round in the nearest whole. Oops, wrong button. So this is 2297. Now we can actually make the appropriate comparison. Now that we have everything in the same type of currency, whether it's the same type as in yen or euros or the same type as in a year. Because the dollar in 1999 was not the same as a dollar today. The dollar in 1929 was not the same as today. You could buy way more things with a dollar in 1929 than you can in 2020. I can guarantee you that. So now we're supposed to determine when these were the most. Where does it say? Where does it say? Were they the greatest? So we're just looking for the biggest number in a completed row. 1,500, 2,300, 2,100. So this would be our answer. The receipts were the most in the year 2000 because this number is the largest. The 2297, that is. If we had turned everything into $1990, this would be like 1,000, I don't know, maybe 1,600 and then 1,500, something like that. And then the 1,600 would be the biggest one that you would see. And again, I'm just guessing. I'm not saying those are right. I could be off by 100 or 200. But the point is that this number in this blank right here would definitely be a little bigger than this number in this blank. If you converted everything to the $2,000, the same thing would happen. The numbers in the middle column will always be larger than the other two columns if they're larger in any particular spot. So that's it. The next guided activity that I want y'all to complete in Canvas is this one. Now, there are some things about this on page 102 and 103 that I don't necessarily agree with on a personal level. And I think that a lot of finance experts would also agree with me there. So let's actually talk about this first. Come on, let me get my annotate on. Financial planning involves saving money for retirement and paying off loans for education and home ownership, which are your home loans are called mortgages. In this table, you are given money ratios from your book, Your Money Ratios, comparing amounts related to your savings and loans. Income and earnings refer to your annual salary. These are suggested guidelines meant to get you thinking about topics. The stock to bond suggested allocation in particular varies widely depending on who you talk to. So this is one of the aspects that I said I wildly disagree with on just my personal kind of retirement plan, what I've learned over the past X number of years and stuff. I've kind of been taught that you should be super aggressive when you're in your 20s, 30s, and maybe even in your 40s, and then be much more conservative later on. That's kind of how you make your pile of dollars as large as possible. And again, I'm not telling you what to do. I'm just saying, what I've learned as an approach. This is someone else's learned approach. So maybe you like this one more. Maybe you like a safer, fiscally safer approach for all of your retirement years, and then you go with this. Nothing wrong with that. So how does this table work? It gives you an age in multiples of 5 up to 65, which is for now when people typically retire, 65, 67. Social Security you can do at 62 or 67, whether you want your full benefit or a partial benefit. This first column right here is your capital to income ratio. Now, they don't have any other numbers here. This is talking about a ratio, one thing to another thing. This is an A to a B. So your capital to your income, they are not showing a second number, so they're writing these as fractions, which means this 0.1 is really 0.1 over 1. So they're saying that your capital should be 0.1 and your income should be the 1. Now, they're not saying that you make $1 and that your capital, the money you've set aside, should be 10 cents. They're saying for every dollar you make that year, you should have 10% of that, or 0.1 of it, put aside into some type of savings, retirement, stocks, bonds, whatever. So if you make $100,000 when you're 25, first of all, kudos on that. Second of all, that means you should, by the end of that year, have $10,000 put away. If you're 30 and making $100,000, that means that you should be saving 0.6 of that, or you should have 0.6 of that set aside, that is to say. So that means you should now have 60 grand in your retirement planning. If you're making $100,000 at 35, you're supposed to have $1.4 for every dollar of that, which means you should now have 140,000 put aside. And I'm going to stop giving away too many answers. the savings to income ratio right here, and again, this says that your denominator would be 1 for a regular number, but these are 100, so this is a ratio is 12 over 100, because that's how percents work, as we'll study in the next 2 chapters. So for every $100 in income, that particular year, you should be putting $12 aside. So it's not, the capital is talking about everything up to that current year. So it's not just age 25, it's not just age 30, so it's all the years combined before should now make up that 60 grand. But in that particular year, you should only be setting aside another 12 grand. So you're setting aside 12 grand when you're 25, you're setting aside 12 grand when you're 30. You're setting aside 15 grand when you're 45. These numbers bump up a little bit, and we'll talk about why. The mortgage to income, this is another one I widely disagree with. You're gonna have, in my opinion, you're going to have a hard time getting a starter home if it's not just a shack, I suppose, where your mortgage is twice your income. If you're making $50,000 a year, that says you can only afford $100,000 in house. I don't know. And I think the problem with this table is this book was probably written like 10 or 15 years ago, potentially, when mortgage interest rates were significantly higher, which then maybe this was a little more relatable. But mortgage rates right now are 3 to 4%. I would say this number for a younger person could be even closer to 3. So that means if you make $50,000 in a year, you could afford a $150,000 mortgage. And again, these are opinions, as is what you see on the screen, and not the point of the exercise at all. The next column, this education to earnings, says if you're 25, then again, this is a 0.75 over 1 if you need to explicitly see the ratio. That says if you made $100,000 that year, you could have $75,000 in student loans. And then at 30, that number shrinks by 35 at 0. And then from 40 on, all these X's, they just mean that they're also zeros. It means you should have your debt paid off by 35. Now, in this world, good luck getting your student debt paid off by 35, with Fannie Mae being Fannie Mae. And again, this is a recorded lecture, so that's all I'm going to say politically. Yeah, and I'll say it sucks. That's all I'm going to say. Talk to me in person if you ever want to hear more opinions. Then the stock to bond, again, this is 25, 30, 35. I will even flat out say I don't have a single penny in bonds. I'm pretty aggressive with my personal investments at a younger age. Those of you who don't know how old I am, I'm 30-something. I'll leave it at that. But by the time I hit 45, I'm going to start getting my bond on. And then when I'm 60, almost all my money is going to be in bonds. And again, this is just how I've personally observed what I think is a good financial plan. Not advice, just telling you what I do. I'm being honest here. And I don't know that you'll get that from a lot of teachers. All right, so they're saying half your money should be in stocks, half your money should be in bonds. What money are they talking about? They're talking about your capital. So when you're 25 and you've got your 10 grand set aside, you should have 5 grand in stocks, 5 grand in bonds. When you're 30 and you've got your 60,000 set aside, you should have 30,000 in stocks and 30,000 in bonds. That's what they're saying here. Okay, so rambling aside, the fact that these 0.1s were 0.1 over 1, and this is 12 over 100, and 0.75 over 1, or 75 over 100 if you want to convert it to whole numbers. You don't need to use any of those fractions if you don't want to. The problems that they're going to have us doing down here, you certainly can, but these are just your Ks. All of these are your K values. These are your multipliers, which will make things a lot easier. So you are 35 years old and you make 60 grand. How much capital should you have? I will do this one and only this one. So, oops, I shouldn't have put it on annotate yet because I got to go back to the table. You are 35 and you make 60 grand, which is pretty good for a 35-year-old in my opinion. It's more than the average American. How much capital should you have set aside at that point? So if you go to the 35 row, so this is the numbers, these are the numbers you're using for all of them. Every single one of these, you're 35 years old, 35 years old, 35 years old for all 6 of them. So they say, how much capital should you have? Well, this is your capital multiplier right here. So that's your K value. So you just take your 60 grand and multiply it by 1.4. And if you do that, 1.4 times 60 grand You get 84,000 bucks. So that says by the age of 35, if you're making 60 grand a year, you should have $84,000 put towards your retirement plan. 401k, IRA, personal brokerage accounts, pension plans, whatever. Do most of us actually have that done? Quite honestly, no. I don't remember my numbers off the top of my head because I usually save this for the end of the semester, but the average 35-year-old's probably got like 10 grand towards retirement at that point. And that's a ballpark guess. No statistics in front of me. And you know what they say about statistics, 86% of them are made up on the spot. As was that 86% value if you didn't catch the joke. Okay. So how much should you be saving this year? Well, that doesn't involve these two numbers exactly. Maybe it involves the 60,000. Maybe it does, maybe it doesn't. How much should the balance of your mortgage be? What should you owe on student loans? How much of your capital should be invested in bonds? By the time you're 65, what salary do you anticipate making? I got to clear my screen. How much capital should you have at that point for retirement? Question 6 is open-ended. This is just a personal question. I don't want to give too many opportunities for that one. In fact, I'm going to scrap this whole thing. I'm going to take this, and I got to make sure that people are paying attention. When you do your worksheets, let's not be 35. Let's be 40. That way everyone has a chance to do 1, 2, 3, 4, 5, and 6. All right, so this will be your next discussion board. And that's page 103. It's 1 through 6. Take 1 only. Do not do 2. I know the last one I gave you opportunities to have discussions and everything, and I need to check on that discussion board and see how they're going. So page 103, these 6, but instead I want you to be 40 years old. Please be 40, and I will point that out. So hopefully everyone's reading the instructions. If I'm going to be honest, I anticipate that someone gives an answer for the 35-year-old, but we'll see how it goes. Okay, so I'll have that typed up. You'll see the discussion board go up at the end of class, just like usual. That will finally close out the chapter. Also, Excel preview 2.4 CPI. This, after 2.1 on currency, this is going to be the next one. So you've got an Excel preview that you can use. Remember, these can be helpful. 2.8 receipts, we're not going to be doing that one. So that's it. 2.5 is on statistics. If you don't remember from the beginning of the semester, I said anything involving statistics, we pretty much skip. And that was page 103, right? 1 through 6. B, the age of 40. 5 exclamation marks. Show its importance. Okay. Chapter 3. Units and conversions. So, guess what chapter 3 is all about? It's all about proportions. Guess what chapter 4 is all about? It's all about proportions. Now, I'm not going to say that every single problem we do is just fraction equal to fraction or y equals kx. And again, those are basically the same two things. When you boil it down, you can solve all those problems using either setup. But that's the idea that we start with. When we talk about the idea of a percent, everything about that is proportional. The way we create percents, when we start talking about part-to-whole comparisons or part-to-part comparisons, it's all proportions. When we want to talk about things like percent change, it's a spin on that idea. It's more of a formula applied to that concept of proportions. But we'll get that. We will get there when we get there. All right, so units and conversions. And if you've had a high school biology or chemistry class, sorry, distractions. If you've had a high school or biology class, then you should have done something called dimensional analysis. You may have even done this in your high school algebra class, depending on where you had school. You may have seen it in another college algebra class, potentially, again, depending on where you had school, because some schools do some things and some don't do some things, right? Not all school systems are exactly the same. That's why when people transfer schools mid-year, weird things happen, information gets lost. Okay, rambling aside. Unit conversion. So what's a unit conversion? All right, Bob went 2 miles. Well, how far did Bob go in feet? How far did Bob go in meters? That's a unit conversion. Or it takes Bob 15 minutes to walk a mile. How many hours does it take Bob? How many days does it take Bob to walk a mile? How many seconds does it take Bob to walk a mile? Those are all unit conversions. Some unit conversion problems are simpler. Some of them are quite involved. Some problems, you only have to do one of these proportions or whatever this dimensional analysis stuff is that I actually prefer. Sometimes you have to do it 2 or 3 or 4 or even 5 times. So the first segue into unit conversions, which goes with the idea that everything in chapter 2, 3, and 4 is based on proportions, is that unit conversions can be set up as proportions as long as you use your words, as long as you write apple over orange to start with, or miles over meters when you start, whatever you might need to do. So that means you cross multiply to solve as long as 3 of the 4 spots are numbers. No new information here. If you make it to the end of this year and you don't know what a proportion is, you don't know how to solve a proportion, you don't understand what proportions mean, that is one doubles, the other doubles, then I'm terrified, because that is one of the 3 main topics we talk about, and we talk about it so much that there is no excuse not to have a hopefully great understanding of it by the end. So you can do this. You can use your words and you can write miles over meters, or you can write feet over inches or whatever. And then you can set up a proportion as long as you know the conversion factor. So a conversion factor is the thing that says 12 inches is 1 foot, or 5,280 feet is 1 mile, or 60 seconds is a minute. Those are conversion factors. And those would be numbers that get placed on one side of the proportion, on one side of the fraction. The other side, you would just put whatever number you have in there. And we'll see examples, don't worry. So one way to do unit conversions is setting up a proportion, fraction equal to fraction. The other way, and this is going to be the way that I emphasize things, I'll do it once or twice as a proportion, but dimensional analysis is a much more efficient method. And the idea behind dimensional analysis, with just getting the right units tells you the answers right, is such a fascinatingly weak but strong statement. There are a lot of ideas in complex mathematics where if you can just do this thing and that thing and multiply and divide by some numbers, where as long as you get the units right, then you're probably right. There are leagues of mathematics that way, where as long as you can get an answer to have appropriate units, then it's probably right, or at worst off by a factor of 2. That's incredible. I can't tell you how much math I've done, and this is a technical name. They call it math on the back of a cocktail napkin, which just means you're just kind of spitballing ideas, multiplying and dividing by things, hoping that you get an answer that's sensible. There are books on this. One of my favorite professors at ODU, he actually co-authored a book involving this, just math on the back of a napkin. And some fascinating topics in there. There's no calculus. It's just all fraction, multiplication, and division. That's all it is, with some insane consequences to the math that's done. Anyways, dimensional analysis. This is a way of converting one unit or rate. We haven't really dealt with rates too much so far. We know that a rate is a ratio, but we haven't played with them. We've just kind of gotten them as answers. We're going to start playing with them soon. So dimensional analysis is a way of converting one unit, like miles, to another unit, like feet, or one rate, like miles per hour, to another one, like meters per second. The main idea is that you will multiply your original value with units in proper spots as a fraction. This is critical. This parentheses note is critical. So you'll multiply your original value by a fraction by a fraction whose numerator and denominator are the two values in a conversion factor. Remember I said conversion factor is the thing that says 12 inches is 1 foot. That's a conversion factor. So in other words, you're multiplying by a fraction that would have 12 inches in the top and 1 foot in the bottom, or 1 foot in the top and 12 inches in the bottom. But how do you know which way to do it? How do you know whether to put the 12 inches in the top or the bottom? Well, that's where this comes into play. You must make sure that in the conversion factor, your old units are opposite the original placement, so they cancel. Opposite meaning if it was originally in the bottom, it needs to go in the top. If it was originally in the top, it needs to go in the bottom. I have this saying that I like. I don't know why it won't let me get back to typing. There we go. Out with the old, in with the new. That's the saying that I like. Out with the old, in with the new. No, it's not my saying. I did not create that saying. I'm sure some other mathematician has used it in this sense, but I did come up with that on my own using that particular saying with this. Out with the old, in with the new means you need to get rid of the old units by canceling, so that way you're stuck with the new units. So we're going to do a problem where we do it as a proportion, where we do it with dimensional analysis, make sure we can get the same answer each way, and that's what this is saying right here. So for instance, 1 mile is 5280 feet. This is a conversion factor. No, you do not need to memorize the fact that 1 mile is 5,280 feet. You will always be given information like this in a test. Now in your homework, you may have to click the view an example or help me solve this to find that, or you may have to Google something, or you may have to look up the table that's in your textbook on page whatever, somewhere in chapter 3. But there's conversion tables all over the internet. There's conversion tables inside of the textbook. There are conversion tables inside of the homework problems as well. Again, on a test, I will not have you memorize anything like 1 mile is 5280 feet. I think some of you would know that, but I won't make you memorize it. I think that every one of you should absolutely know 12 inches is a foot, but I won't even force you to memorize it. I'd give it to you for a test. What I do expect you to memorize is time. So please understand, you must memorize all time conversions, all simple time conversions. Things like 60 seconds is a minute. Things like 60 minutes is 1 hour. Things like 24 hours is 1 day. Things like 365 days is 1 year. Asterisks. You could say it's 365 and a quarter when you want to consider leap years and everything, but we just always use 365. Notice there's no month conversion. Why is there no month conversion? Because the number of days in the month varies wildly. The number of days in a year only varies every 4th year, so we just stick with 365. It's a lot more common. But January is 31, February is 28, sometimes 29. March is 31, April's 30, May is 31, June is 30, July and August are 31. There's a really fascinating way to memorize that, and I wish I was in class. And I can't draw for garbage, so I'm not going to try and draw my knuckles, but if you take your hands, if you make fists with them, like stick your arms straight out, make fists with them, and then take your fists and push them together so that your knuckles are kind of aligned with each other. If you start on your left pinky knuckle, you call that January, that's a 31. Then the dip between knuckles, the dip between your pinky and your ring finger knuckle, that's February because it's a dip, it's not a 31. And then March would be the next knuckle, so it's a knuckle, so it's 31. Then you have a dip for April, 30, then knuckle for May, Then June is a dip, so 30. July ends up being your pointer finger knuckle. And then August, you got to switch hands and you end up on another knuckle, which says August is 31. It's actually really cool. You could probably Google that. I imagine that someone else has said that. But I know I learned that from my mom when I was like 3 or 4 years old and it stuck. The things parents can teach you that you remember forever. All right, so I do expect everyone to know these. I will never, ever, ever give you those, but there's no conversion for month because they're inconsistent. Also, a lot of people will like to say, oh, it's 4 weeks. A week is 7 days, and then 4 weeks is a month. No, 4 weeks is 28 days. The only month that's true of is February. It's more like 4.3 weeks is a month, but you shouldn't use that because it's not super, super accurate. These are the only ones you should be using unless they say to go from days to weeks or something like that. And then 7 days is a week. So again, memorize those. Everything else is given to you. So 1 mile is 5280 feet. So if you wanted to convert 0.75 miles to feet, it would look like this. And I have it typed up below. I want to write it out first though, just to build it. You start with the original value. So we're converting the 0.75 miles. So we have to write that first. You always write the number and the units that you have first. Now that miles, it's not a per. There's no word of per in here or any similar word. So the miles go in the top with the 0.75. So then you're going to multiply this thing by a fraction. And in this fraction, it's going to use this, the conversion factor. So the 1 mile might go in the top, or it might go in the bottom. The 5280 feet may go in the top or the bottom. It just depends. Out with the old, in with the new. You must make sure that in the conversion factor, your old units are opposite their original placement so they cancel. That idea is super, super critical. The old units need to go away. We don't want to see miles anymore. We want to see this converted to feet. So because the original miles were in the top, we know that we need the miles in the bottom. Please notice what I'm about to write first. I'm not going to write the 1 or the 5280. I'm not going to write feet. I'm going to write miles. Or mile. You can pluralize it, it doesn't matter. That's all I've done so far. I didn't even look at any of these numbers. I don't even need to know the conversion factor to know that this is going to need to be there. Because miles were in the top, I have to put miles in the bottom of the fraction, the multiplier, so that they will cancel. That's what we have to make sure happens. So, the first thing I write before anything else is the original units so that they would again cancel. Then I go and start putting numbers in place. So how many miles to how many other things? Well, it's 1 mile, 1 mile. Make sure that 1 goes here. If you put it in the top, it's wrong. And then the other thing is the top, 5280 feet. Everyone makes this out to be something insanely difficult, and it's not. Again, here's that process. Dimensional analysis, multiply by a fraction. In that fraction, old units should cancel. What are the original units? These are my old units, miles. Where are they? They're in the top. If they were in the bottom, it would look like this. It'd be just something over miles. Maybe it's inches per mile. Maybe it's seconds per mile. I don't know. But here the miles would be in the bottom, which means in the multiplier, they'd have to be in the top. But that's not what it was. Okay, so the miles were in the top. So the first thing your brain should go is, all right, out with the old and with the new. The miles are in the top, so it needs to go in the bottom of the multiplier. Then we start putting our eyes on the numbers. 1 mile, 1 miles, doesn't matter about the plural, is 5280 feet. So that says the 5280 feet goes in the top. So when we do this, our miles cancel. There's something in the top and something in the bottom that matches, so they cancel. Then we're just going to do the math. This 0.75 and the 5280 are in tops, so you're going to multiply them. 0.75 times 5280. I'll pull out a calculator. 0.75 times 5280. Boom. 3,960. 3,960. Well, how do we know what our units are? How do I know? Well, I canceled out the miles. The only thing I see left over is the feet. So guess what? That's your units. Do not make something as scary sounding as dimensional analysis actually be terrifying. It's not. It's nothing. Dimensional analysis is nothing in the grand scheme of things. But everyone stumbles with this severely, especially at first. I don't want to say everyone, most people. Because they get so caught up on searching the table for these numbers and then just, oh, I'm just going to put the bigger one in the top, or I'm just going to put the bigger one in the bottom. That's not necessarily the case. You have to pay attention to the placement of things. So this was correct. How do I know it's correct? We say, does it make pi? No sense. Kidding. Well, 0.75 miles is less than 1 mile. So when we convert it to feet, well, 1 mile is is about 5,000 feet. So one of these things turns into about 5,000 of these things. 0.75 is almost 1. It's not too far off from it. So that means this number should be some thousands of feet. It shouldn't be more than 5,000. It should definitely be less than 5,000. But we shouldn't get an answer of like 17 feet or 30 feet or 2 million feet. This is in the sweet spot. It's smaller than 5,000, but it's not too small. Now, the next thing I'm about to do is going to be wrong, 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 wrong. I'm going to show you what happens when you do this wrong. When you pay attention and you do your math correctly, you can tell it's wrong. So what I'm about to do is wrong. Start out with your 0.75 miles. This is not wrong. What's wrong is what I'm about to do. Oh, I'm going to multiply by a fraction. All I care about is the 1 mile is the 5280 feet. So I'll put the 1 mile in the top and I'll put the 5280 feet in the bottom. That's what Mr. Beckner said to do, right? Just make sure you got your conversion factors here. It's a fraction. We're good. Okay. Well, everything in red up to this point is wrong. And here's why. The whole point is out with the old and with the new. The whole point is your old units are supposed to be in opposite locations, opposite meaning top and bottom. These miles are in a top. These miles are in a top. They don't cancel. In fact, guess what happens when you have something in the same location and you multiply it by itself? It stacks. It gets an exponent. If you have a 3 times a 3, that's 3 squared. If you have an x times an x, that's x squared. So the units, I'm ignoring the numbers for a second. This is just the units. That's miles times miles, which gives us miles spelling, miles squared. So the miles times the miles makes miles squared. The feet are still on the bottom. You can't cancel anything. You can't just imagine it's not there. It's there. So the units of this thing, when you do the math, are going to be miles squared per foot. Miles squared per foot. What in the heck does that mean? So here's our brain just exploding. That's not hair, that's our brain exploding because we don't know what that means. Your teacher, who has had many, many, many years of mathematical education, does not know what a mile squared per foot is. This instantly says, no, it makes no sense. But here's the problem that most students have. They just assume everything is hunky-dory and the miles cancel and the answer is going to be feet, and they're not going to pay attention. So you actually have to pay attention to this stuff and make sure that you're seeing the canceling. This is not canceling when two things are on a top. If you do the math, this 0.75 is in a top, this 5280 is a bottom, so that's a division. So here's what the number comes out to. You got 0.75 divide, that doesn't look right, 0.75 divided by 5280. Again, the 5280 was in the bottom, so that's a division. And we end up with this, 1.42 blah, 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 e negative 4. Now, this is scientific notation. That means the decimal goes left 4 times. So left 4 times 1, 2, 3, 4. It ends up being, that's 142, 0.000142. So let's say you nerfed the units. Let's say you didn't get this because you weren't paying attention and you just said, oh, I know my units are supposed to be, not miles, feet. Oh, I know I'm converting some of my answers in feet. Does it make sense that 3/4 of a mile is 0.0001 foot? That's not even an inch. That's not even 1/10 of an inch. That is such a small distance, it's practically immeasurable. That is 0.001 inches. That's 1/1000th of an inch. 0.75 miles is 1/1000th of an inch? No. This is hot trash. This is garbage. So again, that last bit was, oh, I assume my units are feet. Here's my number. But no, it doesn't make sense. It doesn't make sense because that number is way too small. If 1 mile is 5,280 feet, 0.75 miles should be in the ballpark of it. Now, if you're converting units that you have no concept of, no spatial concept of, then you can't make that argument, which means you have to be even more careful in paying attention to the units. But again, that's two different ways to ask yourself, does it make sense on that problem, and discover that it's wrong. Now again, one of those ways, the numerical side, if you're converting something like fluid densities, you're probably going to have a hard time grasping those. And I get that. Or if you're converting across several units, you might have a hard time really gauging the size of that number, which means you really have to pay attention to your units. Okay, so here's just that same math typed out. Your 0.75 miles, your times. We make sure that the mile goes in the bottom. Then we throw all the numbers in. You'll see your miles cancel. The only unit you have left is feet, which is why that's feet. And then the written explanation of everything I just said. Before we get into this next stuff, what if the old, well, actually no, before we get into this next stuff, we'll do the bold note, but not the others. What if the old units were in the bottom originally? What would you put them, where would you put them in the multiplier in order to cancel them? So this example we did previously, the unit that we wanted to change, the miles, was in the top. Now we're saying, what if the units were in the bottom originally? How does that change this fraction and multiplication idea? It doesn't change the original concept. Your old units have to be opposite the original placement. So what that means, if they were in the bottom originally, then the multiplier, the original units need to go in the top. The opposite location. So for an example of this, let's say we wanted to convert 90, no, I'll stick with a more sensible number. Not that that's not a sensible number, but it's not a lot of places you should be driving 90 miles an hour in Virginia. Let's go with one you should be driving on the highway at least. 60 miles per hour to miles per minute. Now that MPH right there, please make sure you know that MPH is miles per hour. Also, please know that MI is miles. I used to always give a test question, and it was basically just ultimately the abbreviation of M. What does it mean? And maybe 10% of my students would confuse M and say miles, but it's meters. M is meters, MI is miles. You've got to know that. So we're going to convert 60 miles per minute to miles per hour. Why would we ever do that? Well, let's say our GPS has gone down, or let's say our cell phone just died and we don't have our charger, and the last thing we saw is we've got to turn off in 5 miles. And there's a lot of different turnoffs that we see. Okay, well, when do we turn? When do we turn? I don't remember the road it was supposed to be. So what you could do is take your speed on the highway right now, which was probably 60 miles an hour. You could quickly convert that to miles per minute, and then maybe using that, you would be able to estimate how many minutes you need to drive to hit that 5 miles. So converting 60 miles per hour. Now per, remember per means the next unit is in the bottom. Lots of exclamation marks for that. So what do? We start out with the original number. We got our 60 miles. That was weird. Every time I hit the button on this pen, it does something different. We had our 60 miles per hour. Now you can extend this fraction bar to be with the 60 as well. It's up to you how you do it, whether you do it this way, with it just being the miles over the hours, or 60 miles on top of the hours. As long as the 60 is in the top, do not do it this way. It's not miles over 60 hours. This would be wrong, wrong, wrong. Okay, so we write our original, and then we multiply by a fraction to make it out with the old, in with the new. Well, how many hours to how many minutes? Well, we should know that 1 hour is 60 minutes. There are no excuses for anyone to not know that in society. All right, so I'm just gonna put the 1 hour in the bottom, then the 60 minutes in the top, and keep going and keep going and keep going. I'm rushing. That's probably not right if you're rushing. Oh, well, we're trying to get rid of the hours. In the last example, we put the hours in the bottom so they cancel. But look at this. The hours are in the bottom. The hours in the bottom, there's not going to cancel. They would stack. This would give it, the units we would get for this would be miles, minutes per hour squared. Again, my brain is literally exploding in front of you right now. It wouldn't make sense. So let's take our time. What is the thing we're trying to cancel? We're trying to go from miles, I'm sorry, not miles. We're trying to go from miles per hour to miles per minute. We're trying to go from hours to minutes. So hours are the things we need to be gone. These hours are in the bottom, so in the multiplier, they need to go in the top. Before I do any numbers, before I even think about the fact that 1 hour is 60 minutes, I can do this because I'm trying to get these hours gone. They're in the bottom. So our multiplier, it's in the top. Then we use the conversion factor. Okay, where's the 60 go? Where's the 1 go? I don't know. The 1 probably goes here, right? No, it's 1 hour. 1 hour is 60 minutes. The hours will cancel, and then we just do our math. This 60 on the left is on a top. This 60 is on a bottom. So we're dividing, and 60 divided by 60 is 1. They just cancel. So we get 1. That's what the 60 divided by the 60 do. Now, the minutes are not the only unit left over. The miles are also there, and some units are in top, some units are in bottom, so you've got to be very careful here. The miles are in a top, so they go in a top. The minutes are in a bottom, so they go in a bottom. So that says 60 miles per hour is equivalent to 1 mile per minute. So if you're driving 60 miles an hour, that means equivalently every minute you're driving 1 mile. So if your turn's in 5 minutes, it's pretty easy to do, if your turn is in 5 miles, if you're driving 1 mile per minute, it's pretty easy to deduce that you need to turn in 5 minutes. That would make it very simple. Now that math wouldn't be quite as easy if we were driving 65 miles an hour, 70 miles an hour, 62 miles an hour. I was just trying to drive home a point. Because guess what? Your cell phone can die, and your charger could be broken or left at home. And in this world of GPS for everything, this is a long lost skill. So we have now seen an example where original units were in a top. So in the multiplier, the original units go in the bottom to cancel. We've also seen an example where our original units that needed to go bye-bye were in a bottom. So in the multiplier, they go in the top. This is dimensional analysis. This is how dimensional analysis works. You write your original value. Then you multiply by a fraction. This is not a proportion how we've done the math so far. I'm going to show you that alternate approach next. This is not proportions. This is dimensional analysis. They're two different things, but both of these different things work to get the job done. So let's go back to the original problem, converting the 0.75 miles to feet, and let's see how that would have looked like as a proportion. So the alternate way, using proportions. Do you think your math teacher cares which way you do this? Absolutely not. If you want to do proportions every single time, as long as you can get them right, fine by me. If you want to use dimensional analysis every single time, as long as you can get them right, that's fine by me. I don't care how people get a job done as long as they get the job done. And in a legal manner. Okay. So we're converting the 0.75, was it miles? Yes, miles to feet. Where again, we know 1 mile is 5280 feet. So using proportions, this is when we're going to need to use our words. We're converting from miles to feet, so I could write miles over feet, or I could write feet over miles. It does not matter. You can do it either way. Remember, proportions, there's 8, arguably 16 ways to set these up. So you can write miles over feet, or you can write feet over miles. It just makes the proportion look different. And I'm only going to actually solve one of them, and I'm going to solve the miles over feet version. So miles over feet. So the first fraction you should write is the conversion factor. And it matters whether you put the 1 in the top or the 5280 in the top. It matters based on this. I have decided to put miles on top of feet. So the 1 goes in the top and the 5280 goes in the bottom. I don't write my units inside of proportions because they're assumed. Anything in the top is miles, anything in the bottom is feet. Again, this is different math than dimensional analysis. The other side is where we would put the known number. Which one do we know? We know the 0.75 is miles, so it has to go in a mile spot. Where are the miles going, top or bottom? Well, they're going in the top. So the 0.75 goes in the top, meaning the bottom is our unknown, and that's where our X or N or whatever letter you like goes. It doesn't matter what letter you use. Then you cross multiply, and you'll get 5280 times 0.75. I'll show the work. Oops, 80 times 0.75 equals 1 times x. Guess what 5280 times 0.75 is? It's 3960. We literally did that math earlier. 0.75 times 5280. So 3960 is equal to x. But remember, just because you have the x equals doesn't mean you're done. You're supposed to write your answer with units. This is not an acceptable answer. This is not an acceptable answer. This is not an acceptable answer. The answer is 3960 feet. Units are critical. Bad things happen when units are converted improperly. Bad things happen when you don't write units in your answers. Very, 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 very bad things. There's a story about how one of the reasons that the Challenger exploded was because someone didn't convert their units properly from one thing to another thing. And I'm not going to say the specific details because I don't have them off the top of my head, and I don't want to be misquoted on a video. In a math class, you don't convert your units properly. Oh, okay, you lose some points. Big deal. In the real world, when you do things wrong, there are consequences. Sometimes dire consequences. So this is something that is very, 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 very important that is just kind of glossed over by some people. All right, so before we get into the more complicated types of conversions using this stuff, let us go to our worksheets. Chapter 3. Um, I'm not gonna go through all of these, and I probably need to zoom in just a little bit. Oh, this is gonna be frustrating. Because of the way this is designed, I'm gonna have to have this pulled back really far because I'm gonna need to look at this table while writing on the screen at the same time. I didn't realize that these were on two different pages. That's okay, we'll make the best of what we can with what we can. Before that though, while I'm actually using this space, in this table, the first thing they ask us to do is to show how we could use a y equals kx setup for this. If we were going to just be doing a whole bunch of these going from one to another. So they say, all right, here's 1 centimeter is 10 millimeters. So your y equals kx, instead of using fraction equal to fraction, if you just wanted to use that constant multiplier with the constant of proportionality that we've showed you how to find using by starting with a proportion, and remember that k could be two different values. It could be 10 or 1/10 in this instance, depending on which way you have it solved. But if you're solving for the m, which they're saying m is millimeters, kind of poor notation, that's the millimeters, c is the centimeters, but at least that's a good clue. You could find the number of millimeters by taking 10 times the number of centimeters, because 1 centimeter is 10 millimeters. So that's how you get this. If you wanted to go between inches and centimeters, just kind of extrapolating, the centimeters thing is what went on the side by itself. So we'd have the inches on the side by itself. The 2.54 is the multiplier. And then the centimeters would be the other thing it's equaling to. So you get c equals 2.54 inches. Or this next one, going from meters to feet, you could say that meters is equal to 0.3048 times the number of feet, which we'll do with an F. The next one, inches to feet, you could say that the number of inches is 12 times the number of feet. So not only can you do dimensional analysis for conversion, not only can you do proportions as fraction equal fractions for conversions, you can also use this y equals kx setup to do conversions. But this is not the way I like to emphasize things, because a lot of students struggle with which side the 12 would go on. So if you find yourself struggling with that, don't use this type of setup. Do fraction equal to fraction or do the dimensional analysis, whichever one you're most comfortable with. But that's 3 different things we've now shown you how to do. And if you think you've got it wrong, then try plugging in the 1 and see if this is right. If you plug in the 1 inch, if you put a 1 here, 1 times 2.54 is 2.54, and 1 inch is 2.54 centimeters. If I had this wrong, if I said I is equal to 2.54 times the number of centimeters, okay, well, 2.54 centimeters is supposed to be 1 inch. If you put 2.54 in for the C, then you get 2.54 times 2.54, which is definitely not 1. It's what, 6.2 something, I guess? Hold on. 6.45, excuse me. I was close. So the next one, you could take the number of yards times 3 to get the number of feet. You can take the number of meters times 100 to get the centimeters. This is really cool, but again, not how I'm going to emphasize things. What we're going to go to and again, sorry for having to zoom out so very, very much, but it is what it is, and that's all that it is. We're going to convert the following with 2 decimal accuracy, which means they want all the answers to have 2 decimal places. 6 feet to meters, 64 inches to feet. I'm not going to do every single one of these. I'm going to leave a couple for the guided worksheets for the discussion board, if you will. But I do need to put on annotate. Put on annotate. Thank you. Convert 6 feet to meters. My screen's hiding some of these. There we go. Converting 6 feet to meters, and I'm going to have to write kind of small. We start with the 6 feet, and I'm only going to do dimensional analysis. So here's our 6 feet, and we're going to multiply by a fraction. And in that fraction, we need the conversion between feet and meters. We got to find that in the table. Now, I said you don't have to memorize these. They'll always be in a table or on a formula sheet or on the internet. So feet to meters, feet to meters, feet to meters. Here's 1 foot is 0.34 meters. So you could use this one. We also have 1 meter is 3.281 feet. So very often, very often, we will see two different conversions between the same two units. 1 foot is 0.3 meters, or 1 meter is about 3 feet. Which one should we use? Guess what? It doesn't matter. It doesn't matter. And I'll even show it both ways to show that it doesn't matter. Let's use the top one first. So I'm gonna just make those a little smaller. So again, I'm using this one, and then where's my other one? 1 meter. So these are the two that we could use. We could use either or, but not both. So in this multiplier, I'm going to do the top one first. So 1 foot is 0.3 meters. Before I even look at the numbers, I don't need them. I'm going to ignore the numbers that I just said. We're trying to get rid of feet, so I know feet go in the bottom because they're originally in the top. If we're trying to convert to meters, I know meters have to go in the top. Then we can put the numbers in place. 1 foot is the 0.3 blah, blah, blah meters. So here's your 1 foot, and here's your 0.3048 meters. And then we just do that multiplication. Again, I can't pull up my calculator, unfortunately. I'm sorry, but 6 times 0.3048 is going to give us 1.8288, which when rounded to 2 decimal places is 1.83. The feet have canceled, so now we're in meters. Alternatively, let's take that 6 feet. Let's multiply by a fraction, and in that fraction, let's, instead of using the fact that 1 foot is 0.3 meters, let's use 1 meter is 3 feet with all its decimals. Now again, before I even start thinking about the numbers, we're getting rid of feet. That was in the top, so feet go in the bottom, so they'll cancel. We're converting to meters, so that should go in the top because we have that conversion factor. And we're going to say 1 meter, the 1 goes with the meter this time, is 3.281 feet. Now, this time, the feet still cancel, but the 6 and this 3 value, last time the 6 and the 0.3 were both top, so we multiplied. This time we're dividing. This is 6 divided by 3.281. If you multiplied those, you'd get 18 something, and that wouldn't make sense. Taking 6 divided by 3.281, sorry, I typoed, 6 divided by 3.281, we get 1.8287, blah, 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 which is 1.83 meters. The same answer. So did it matter which of those two conversion factors we used? No. Do you always get 2 conversion factors? No. But sometimes you do, and it makes you go, which one am I supposed to use? It doesn't matter as long as you out with the old, in with the new, as long as you make sure that your old units will cancel and you get your new units. If you don't like doing dimensional analysis, you could have done this as a proportion. This will be the last time I show it. You could have said, all right, I'm converting from feet to meters, so I'll put feet in top and meters in bottom. So that's how I'm going to write my fractions. So proportion, fraction, equal, fraction. What's our conversion factor? I'll only show it with the top. 1 foot is 0.3 meters. So we go 1 foot is the 0.3048. Then we know this thing is 6 feet. Where does it go? Does the 6 go in the bottom? Well, that's meters, so no, that would have been wrong. The 6 has to go in the top. That was weird. Meaning there's an x in the bottom. You'll cross multiply. You'll get x times 1 equals 6 times the 0.3, and that's 1.83. Same thing, but you can't just say x equals 1.83. You'd have to say 1.83 meters. You need your units in your answers. If you had me for developmental math by chance, you heard me make this speech. I don't care about units and being written in answers in developmental math so much. I care about it in quantitative analysis and quantitative reasoning. Because 1.83 is not an answer. What are you talking about? 1.83 light bulbs, 1.83 Bob Doles, 1.83 dogs, 1.83 meters. Super important. All right. This is going to be a challenge coming up, but I'll do the best I can once we get to C. Just because I got to write really small to the best of my ability. So 350 centimeters to feet, centimeters to feet, centimeters to feet. Is there anything up here that goes from centimeters? I'm sorry, I'm looking at C because I said C. We're still on B. We're on B, excuse me. We're here. We're here. I got excited. 64 inches to feet. Well, you should know, in my opinion, how many inches to how many feet. But if you don't, it is up here that 1 foot is 12 inches. So we're going to use this one for B. So we start out with our 64 inches. That inches is in a top. All of these are in tops. There's no pers, so none of them are in bottoms. So times. Then you're multiplying by a fraction. Out with the old, in with the new. So the original units were inches. The original units were in the top. So in the multiplier, they must go in the bottom. I do this before even looking at any of these numbers. I know I technically looked at them earlier, but you get the point. I'm not trying to force the numbers in here yet. And we're converting to feet, and there is a thing that goes between inches and feet. It's right here. You don't always get a direct conversion, spoilers for C. Sometimes there's a middleman. So if there's a middleman, I couldn't put feet in the top, but there isn't, so we can. So how many inches to how many feet? Well, it's 1 inch to 12 feet, right? No. I'm doing a lot of things wrong intentionally to keep you on your toes. It's 1 foot is 12 inches. Pay attention. Okay. What happens? Inches, gone, out with the old. The 64 is in the top, the 12 is in the bottom, so we're dividing that. And when we do that math, 64 divided by 12 is 5.33 when rounded. And if you write 5.33 as an answer on a test, if the units aren't already written there for you, guess what? I'm going to mark that as wrong. You'd get partial credit, but it's wrong. 5.33 what? 5.33 ice creams? That sounds awesome. Yes, give me that. No, it's 5.33 feet. 64 inches is not 5.33 ice creams. 5.33 feet. That makes sense. Check this out. If you would multiply the 64 and the 12, if you accidentally multiplied 64 times 12, you'd get 768. Does that make sense? No. 64 inches is not 750 feet. The things that you can ask yourself, if the sizes are right, ask yourself. If it's a lot more convoluted and confusing, like converting from kilometers to miles, you might not have as good of a grasp on that. But when you can, analyze. All right, C, this is where things get interesting. Centimeters to feet. I see centimeters to millimeters. I see centimeters to inches. But I don't see centimeters to feet in here. So with C, there is no direct conversion of centimeters to feet. Now, if you Googled this, you can definitely just Google what is the conversion from centimeter to feet, and it gives it to you, but that's not what we necessarily want. We want you to understand how to go through multiple layers of this. This is going to require more than one of these fraction multipliers. So here's what happens in this instance. You're going to need to convert from centimeters to a middleman. You're going to have to go from centimeters to a middleman, maybe another middleman, and then ultimately end up at feet. So we've got to find something going from centimeters to something else. Then we got to find something from the something else to feet. So we got to go from centimeters to something. Then we got to go from the same something to feet. And there could be more of these. It could be from the same something to something else, then from that something else to feet maybe. And I have an example that I'll show you that really emphasizes that. Okay. So we write our 350 centimeters. I'm going to do this above. 350 centimeters. We know we got to multiply by a fraction. We know we got to multiply by a fraction. And we're trying to get rid of centimeters. So we know the centimeters go in the bottom because they're originally in the top. Before I even look at the table at all, I can set this up. Now we go to the table and we say, oh, okay, well, there's no centimeters to feet connection directly. So what we have to do is go from centimeters to middleman, then middleman to inches. Well, the only two things we have for centimeters are centimeters to millimeters, but I don't see anything up here that then goes millimeters to feet, so that sucks. But we also have inches to centimeters and meters to centimeters. Inches to centimeters, we know that we could go from centimeters to inches, and then we could go from inches to feet because we've even used that one. 1 foot is 12 inches. So we could use this combination. I'm going to do a couple dots and then erase them. We could go from centimeters to inches. We could use this one as our first. And then we can go from inches to feet. That's one way. Or we could go from centimeters to meters, which is right here. So I'll do this in a different color. We could go from centimeters to meters. This would be the first. And then we can go from meters to feet using this one. It's all about tracing a path, finding a middleman that has a connection. I'm going to do the blue version, but the orange version would be correct as well. Try that on your own, in fact. So we're going to do the blue version. So we're going to say that 1 inch is 2.54 centimeters. Well, the centimeters goes in the bottom, which means the inches are in the top. And we said it's 1 inch is 2.54 centimeters. Pay attention to put the numbers in the right spot. Now that means the centimeters will cancel. And we're going to have an answer in inches, but we need an answer in feet. So we need to do another multiplier. And I'm going to show this multiplier in black. So we got to multiply by another fraction where we're going from inches to feet. That's where the second one comes in play, that 1 foot is 12 inches. We know we're trying to get rid of inches. The inches are originally in the top, so they go in the bottom, which is the feet go in the top. And we know 12 inches is 1 foot. That cancels the inches, and the only unit we have left over is the feet. This isn't something absolutely crazy. It's not some super berserk formula. It's not calculus with layers of algebra. It's fraction multiplication in such a way to cancel whole units. This is simple math that with practice you can master, but without practice, you're not going anywhere. Now the 2.54 and the 12 are in the bottom, so those count as divisions. I'm just going to show you what I'm about to do. 350 divided by 2.54 divided by 12. That's what I'm about to type in my calculator. 350 divided by 2.54 divided by 12. And you get 11.48 when rounded to the nearest tenth. Someone's calling me as I try and use my calculator. That was 11.48, yes. 11.48 rounded to the nearest tenth. This is not an answer because it doesn't say units. What are the units? Feet. You might have a harder time making sense of this one, but a centimeter is a small unit of measure. A foot is a larger measure of units. So this number should be bigger. If you multiplied them, you would get 350 times 2.54 times 12. You would get 10,000 and some change. 350 centimeters, 350 tiny things is not 10,000 large things. Ask yourself, does it make sense? Now, how much sense it makes to you, that can vary from person to person. All right. Let's do D next. 149.6 kilometers to miles. Now, we know when we start writing this out, our 149.6 kilometers we know in our fraction multiplier we got to get rid of the kilometers. The kilometers are originally in the top, so they go in the bottom. Now let's see if we can convert directly from kilometers to miles. Is there a kilometer to mile conversion up here? Let's see, centimeters, inches, feet, yards, meters, furlongs. What the heck is a furlong, right? Well, there's the conversion. It's 660 feet. I'm not asking you to know that or memorize it. It's just numbers. That's all it is. All right, here we go. 1 kilometer, 1,000 meters. That's not what we're looking for. 1 kilometer is, ooh, here we go, 0.6 blah, blah, blah miles. So kilometers to miles. Here's one we could use. But notice that they also have this one. 1 mile is 1.6 kilometers. We could say that 1 kilometer is 0.6 miles, or we could say 1 mile is 1.6 kilometers. These are the same conversion factor with numbers, with different numbers, of course, but it's the same conversion factor because one thing is equivalent to the other. You know why we have 2 different versions of this? So you can have 2 of the different y equals kx formats. You could have one of them solve for kilometers and one of them solve for miles. And then these are just the multipliers in those scenarios. Also, another way of thinking about this is that you've got different things scaled to 1. This is the conversion factor with kilometers scaled to 1. So for every 1 kilometer, that's how many miles it would be. Or this is the conversion factor with the miles scaled to 1. So for every 1 mile, it's 1.6 kilometers. So if you wanted to say, well, what's a 5K in distance? You know, 5K, 5 kilometers. Well, you take the 5. Since we're going from kilometers to miles, it'd be better to use this one. You can just have that as your multiplier. But if you wanted to convert 3 miles, or particularly 3.1 miles, to how many kilometers is it, this would be the better multiplier because you're going from miles to kilometers. But again, I'm not actually doing any of that. I'm doing dimensional analysis. That's my favorite version. All right, so out with the kilometers. Which one are we going to use? Any preference? Well, last time I went with the top option. Actually, no, I do have a preference. I'm going to use the top one still. The bottom one's okay. I like this one because the miles, this number right here, because that's the miles. Miles go in the top of this one. It means we'll multiply these instead of dividing them. That just makes the math easier if you didn't have a calculator. So 0.6214 miles is 1 kilometer, but I could have written 1 over 1.609 if I wanted to use the second one. That cancels our kilometers, and when you do this math and round to the nearest hundredth, you should get 92.96. Miles. So 150 kilometers is about 93 miles. Okay, let's do E. And that'll be the last one I do. So E is gonna be the last one we do. 1,000 millimeters to meters. Now, some of you might know that 1,000 millimeters is a meter and you can do this super quick. So some of you, I'm just gonna do this to the easy way to the side, easy E. No, not the wrapper. The easy way to do E, if you just happen to know this conversion, 1,000 millimeters. Oh, I know 1,000 millimeters is a meter, so we put our 1,000 millimeters in the bottom, so out with the old is 1 meter, in with the new. The thousands cancel and you get your 1 meter. But that's not in this table anywhere. You'd have to know that or have Googled it or something like that. The table has a double conversion scenario. We're gonna have to go from millimeters to centimeters first, and then we're gonna have to go from centimeters to meters. That's how this table has it set up. This table is a little bit of a nuisance in that regard, but it gives us enough information to do it. So if you knew this fact, it would make it more efficient, but it still works. So here's our 1,000 millimeters. We'll multiply by a fraction. So we got to go from millimeters to centimeters, where 10 millimeters is 1 centimeter. Out with the old, we know millimeters in the bottom, centimeters in the top. And we said it's 10 of these millis is 1 centi. Millimeters are gone. Okay, now the next one, so times. We got to get rid of the centimeters. We're now using the fact that 100 centimeters is a meter. Out with the old, so centimeters in the bottom, meters in the top, and 100 of the centis is 1 milli. Cancel, cancel. 1,000 divided by 10 is 100, 100 divided by 100 is 1, and you end up with 1 meter. Same answer. So F, G, and H, I'm going to leave to the discussion board. F, G, and H. So for the discussion board, it'll be F, G, and H. I'll even give you the approximate answers, just so we know whether we're right or not. F is 4,000 something, something, something. G is in the ballpark of 90 to 95. H is in the ballpark of 5,000. I'm not saying it's 5,000 something. I'm saying it's about 5,000. It might be 4,500. It might be 5,200. So remember, with the discussion board, show your work, talk about what you've done. I know it's going to be hard to type out fraction multiplications. Just try and say it as best as you can. So you could say, in the top I did this, in the bottom I did this. Now, if you did this with proportions, that's perfectly fine. If you don't like dimensional analysis, if you want to do every single one of these with a proportion, then you can. Please note that the ones where I had two multipliers, like in E and C, that means you would have to do a proportion twice. Particularly for C, you'd have to do a proportion going from centimeters to inches. Then you would have to do a whole new proportion going from inches to feet. So I just think that's less efficient. Does it work? Yes. Is it slower? In general, yes. So that'll be the next discussion board, and that's page 118, 119. So right now we've got about 9 questions for that discussion board. That's enough for everybody to do one. So nobody needs to double dip on that one. All right. How much time we got? 15 minutes. Let's clear our screen. So I'll add that to the notes. That was page 118 and 119, right? Not that. This. And that was problems F, G, and H. Again, I even gave you ballpark answers, so you should know if you're right or wrong when you're doing this. All right. Before we get to the next little section of this, the units is squared, blah, 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 blah. Let's do another random example that I like to do. Convert 2 years to minutes. Convert 2 years to minutes. Before we do anything, ask yourself, do you think this number is going to be really big or really small? That's what you should be asking yourself. And hopefully you come up with really big. 2 years is a lot of minutes. So we start out with the 2 years. And then we're going to multiply by a fraction. Now these are the ones I told you that you should have memorized. No excuses. So you might say, well, let's go from years to months, because there's 12 months in a year, and then we can go from months to days, and then from days to hours, and then hours to minutes. Well, here's the problem. We don't know how many months to how many days. It's 30 and some change on average, but it's not exactly 30. So we can't use months. We got to go from years to days, and we know there's 365 days a year. That happens enough that we can just say that's a fact, 365 days a year. Well, out with the old, which means years go in the bottom, in with the new, days go in the top. 1 year is 365 days. But then we need another, because now we're in days. The years are gone. We can go from days to hours. So in this one, out with the old, days in the bottom, hours in the top. How many days to how many hours? Well, 1 day is 24 hours. days are gone. Now we got to multiply by another fraction to go from hours to the next thing. Well, we can go from hours to minutes. So out with the old, hours go in the bottom, so they'll cancel. Minutes go in the top. Hours are gone. How many hours to how many minutes? Well, 1 hour is 60 minutes. That's the units we want, so that'll give us our answer. So we're just going to take the 2 times the 365 times the 24 times the 60. 2 times 365 times 24 times 60. 2 times 365 times 24 times 60. 1,051,200. 1,051,200. And that's our answer, right? Nope. Why is that wrong? Units. Minutes. 2 years is about 1 million minutes. Do you know why we talk about time on the long scale in years instead of minutes? It's really hard to grasp 1 million minutes. It's a lot easier for us to grasp 2 years. That is one of the many reasons we have dimensional analysis, because sometimes the numbers get just too big to be comprehensible, so we need to have some other type of units. We go from meters to kilometers, or from feet to miles, or from minutes to years. Can you imagine what this would be if it was seconds multiplied by 60? That's an even bigger number, 60 million and some change. Maybe 61 or 62 million. I'm curious. 1,051, 200 times 60, 63 million. That's what I had in my head after I started doing the math. 63,072,000 seconds. Okay. I'm going to skip a little bit right here, this line. This is something I mentioned earlier. You don't have any dimensional analysis to memorize in terms of converting units, except time. So if it asks you to convert from feet to meters and you don't know it, if you click view an example, it's generally in there if they didn't give you a table to begin with. If it's not in there, then go to your textbook or go to Google. On a test, you would have a provided formula sheet that you could use for that. Okay. If a unit is squared or cubed, you have to multiply the conversion factor that many times. This right here throws so many people off. 1 foot is 12 inches, so then they think, oh, 1 square foot is 12 square inches. That's completely wrong. And that's a big problem if you ever want to go and retile your floor and you think, oh, okay, well, I measured my house, my floor, and it was, say, 10 by 12. So that's 120. So I need, 120 square feet. Then just multiply that by 12, and you think you only need 1,400 square inches. And then you go to the store and you're like, wow, I don't even need a whole stack squares. And then you get home and you start laying them out, and you're, I wasn't even close on my math. I goofed. That's where issues like this come up. Converting squared or cubic units from one type of thing to another type of thing, from, like, say, square feet to square inches, or cubic meters to cubic miles even. If you are dealing with squared units, you have to multiply a conversion factor twice. If you're dealing with cubed units, you have to multiply by the conversion factor 3 times. Here is why. Worry about the alternative later. Let's say you wanted to convert, let's just go with, did I do with 1? Yeah, we dealt with 1 earlier. 1 square foot to square inches. So 1 square foot is how many square inches? And we already saw the answer below, but let's show that using this way. So you start out with your 1 feet, not 1 feet, 1 squared foot, or 1 foot squared. and we got to multiply by our conversion factor. Okay, well, we know that 1 foot is 12 inches. So if we do this multiplier, out with the old, our feet were in the top, so we got to put the feet in the bottom. And you might say, oh, okay, well, just let me put squares on both of these. And that's not how squaring things works. You'd have to square both sides, which is what you see down below, but let's ignore that for now. So that's not true. It's 1 foot is 12 inches. So out with the old, feet are gone, inches in the top, that'll be the new. 1 foot is 12 inches. Now, when we were doing our canceling previously, we canceled an hour with an hour, gone. Or we canceled a years with a years, gone, or a days with a days, gone. These are not completely canceling. Feet squared and feet do not cancel. This feet will cancel one of them. With feet squared, that means there's 2 of them. There are 2 of these feet here to be canceled. We're only getting rid of 1 of them. So that 1 foot squared is now a foot to the first power. So now we have inches and feet. That's not good, which is why we have to multiply the conversion factor a second time. We have to do this 12 inches over 1 foot an additional time. Now this feet in the bottom will cancel with the foot to the first power in the top. We have inches here, we have inches here. So the units is not inches. This is not correct because we have inches times inches. Anything times itself is itself squared. And then the math is 1 times 12, which is 144. So 1 square foot is actually 144 square inches, not 12. A foot is 12 inches. A square foot is 144 inches. A cubic foot means you'd multiply by 12 again. A cubic foot is 1728 cubic inches. So when you talk about measuring a volume, those units get even further and further removed from each other. It's kind of crazy. So this is one way of converting squared or cubic units, and you will see this in your homework. You can see this on a test. It's not as numerous, it's not as frequent, but you will see it. I can promise that. Squared and cubic units are important. We measure lots of things with these types of units. All right, so what's that alternative thing say? Alternatively, you can square or cube both sides of your conversion factor to get a new conversion factor. So this typing below, I'm going to show you the writing. So here's the original factor. 1 foot is 12 inches. And oh, well, we're dealing with squared units though, so let me square both sides. So here's how it looks. You square both sides like so. That was a weird looking parentheses. It kind of looks like a 2. This is me squaring both sides. You're not just squaring the units, you're also squaring the numbers. This squares the numbers and units. That's how that math works if you haven't been taught it, and that's why I give you alternate versions in case you haven't been taught this. So what this turns into is, well, 1 squared is 1, so that's 1 foot squared. 12 squared is 144, and then you have your inches squared. So 1 foot is 12 inches, that's a singular conversion. Now we have, in squared units, a single conversion. 1 square foot is 144 square inches. So we could go back and take our 1 square foot, and we can multiply by 1 square foot in the bottom is 144 inches squared in the top. The feet squared cancel with feet squared. 1 times 144 is 144. So we get the same thing. Do you think I care which way you do it? No. I'd love for you to understand both ways, but as long as you have one way that you understand, then we're all good. That's what's important. The final thing I want to point out is that temperature conversions work differently because they are not proportional. Remember, the idea of proportions are if you double one, the other doubles. There's another important issue of that. Remember, proportions mean double, one, the other doubles. Also, that means that 0 in one version is 0 in the other version. Otherwise, the doubling aspect doesn't work. Because if you have 0, if 0 degrees Celsius is 32 Fahrenheit, if you double both of those, well, 2 times 0 is 0, and 2 times 32 is 64. Well, 0 degrees is 32 degrees. Sorry, 0 Celsius is 32 Fahrenheit. It's not possible for 0 Celsius to also be 64 Fahrenheit. So temperature doesn't follow this rule because they're not zeroed out, and also because doubling one doesn't double the other necessarily. They have, it's like a 9/5 or 5/9 depending on which way you have it set up. So there's a formula instead, and you do not have to memorize the formula. You just got to know how to use it. And that formula is C equals 5/9F minus 32. You don't have to memorize this. It would be provided to you. So the minus 32, this is the thing that makes it not a proportion. That single number with it as a constant. Because proportions are like a y equals kx. So the c is like the y, the f is like the x, and the 5/9 is like our k. But you can't have a plus or a minus another number. All that stuff about proportions falls apart. So temperature conversions are the odd man or odd woman out in that they're not proportional. It's a formula that must be memorized. And there are other types of conversions in the real world that work this way as well, but we don't deal with them in quantitative reasoning. Most of our conversions are proportional, with the exception of temperature. All right, worksheet. We got a few minutes left. We're skipping that. Let's just do A and B. So this is on page 122, guided activity 1 with temperature. Here's that. And they write theirs. Wait, what did I write previously? I think I may have written something wrong. Yeah, I did. This is not right. See, you know what happened was I was looking at the guided activity trying to figure out where we were, and I was trying to write something at the same time. That's what happens when you multitask. The formula is F equals 9/5C plus 32. That's one of them. Or C equals 5/9 parentheses F minus 32. I forgot my parentheses. That's what happened. Those are the two formulas, but I only have to give you one of them. I don't have to give you both because you should know your basics of algebra. Now let's go back to the worksheet. So using this formula, and this is the same thing as what we had before. Convert the 40 degrees Fahrenheit to Celsius, convert the 80 degrees Fahrenheit to Celsius. So 40, I think we all would probably think is kind of cold. Some of us might disagree. 80 is warm. Maybe some people would say hot. Again, that is, you know, subjective. But when I say 40 and 80, when I talk about temperature, everyone in America, when I say 40 or 80, they're going to think I'm talking about Fahrenheit. But it's not really appropriate. In a quantitative reasoning class especially, I shouldn't say the temperature is 80 outside right now. I should say it's 80 degrees Fahrenheit, because 80, are you talking about Celsius? Are you talking about Fahrenheit? Are you talking about Kelvin? Because if it was 80 Kelvin outside, we'd be frozen in place. We don't even talk about Kelvin in this course. But anyways, we're just going to take the 40 degrees Fahrenheit and plug it into the F here. So annotate. We get C equals 5/9 times 40 minus 160/9. And then you can just do your math. The 5 divided by 9 times the 40 is going to be 22.22, 222, etc., minus 160 divided by 9 is going to be 17.77. And if you actually just do that all in one, you should get 4.44444 when you do that subtraction. We're going to round this to 2 decimal places because that's what they tell us. So 40 degrees Fahrenheit is 4.44 degrees Celsius. 80 degrees Fahrenheit, C equals 5/9 times 80 minus 160 over 9. That's 5 divided by 9 times 80. That's 44.44 minus 160 divided by 9. You end up with 26.66. I'm not going to show the middle work this time because we're about out of time. So 26.67 when rounded appropriately degrees Celsius. Now what C asks us is, did doubling one double the other? And the answer is no. Doubling 40 to 80, well, we got 4.44 and then 26.67. That definitely didn't double. It went up way more than doubling if you thought about it as a proportion. So that emphasizes that temperature is not proportional, as we've said. And then part F, which you can't see, I'm sorry, part H on the screen, you can't see on the screen, I need to clear it. Solve the equation for F as a function of C. That's what I gave you earlier in the second version, F equals 9/5C plus 32. I actually prefer that equation overall, but they're both good to have. There's nothing wrong with having both. It's just one looks a little prettier than the other. It's also easier to write as a decimal because 9/5 is 1.8. 5/9 is not a pretty decimal. It's 0.5 bar. Okay, so that's 3.1, which means 3.1 homework is due in a week. I said we'd finish it, and we did. 3.1 due. I don't have that due date set up yet, but I will. I'll also have those discussion boards set up in just in another 10 or 15 minutes. This video should be uploaded in the next half hour. Remember, your next Excel assignment due is BMI on the 16th. That's coming up shortly. Hopefully you have already tried to make that multiplication table on your own. That's completely separate from the BMI. That was a suggestion to make sure you can understand your fixed cell references. If you're having a hard time understanding that, go back to the video where we discuss that. Remember, I said it's a good idea to take notes on when we discussed things, because I make the descriptions pretty general on YouTube. All right, so that being said, have a good one. Have a good weekend. Work hard, work hard, work hard. Remember, 8 or 9 hours every week outside of class. That's the expectation in the summer. So good luck to you. Study hard. As I said, project discussion is going to be in a while. We're not getting to that yet. Test, midterm, we don't need to talk about that for a while because that'll be up to chapter 4 and we still got some time. So have a good one. Email me with any questions.